Okay, so good afternoon, everybody. Recording is started. Kevin or Eric, not here? Okay. All right, so today we're going to talk about sections 2.4 and 2.5. Should go relatively smoothly. And I guess we're starting to sort of get to the point where we're actually talking about calculus. So Chapter 3 is really going to be the meat and potatoes of the section of the course that's going to be on derivatives. Hang on a second. Bay, right?
Yes.
Do you go by Bailey or Bay?
It doesn't matter.
Doesn't matter. Okay. Okay, so we're getting to the meat and potatoes of the derivative part of the class, okay, in Chapter 3. So far we kind of learned this like really annoying way of calculating derivatives where we take the average rate of change over smaller and smaller intervals. Soon we're going to learn some much better ways of doing it that are going to be far easier than that and far more convenient, okay? And then we're going to start analyzing, okay, what does this derivative tell us? How do we interpret it in the context of word problems and those sorts of things? So that's kind of the big picture vision of where we're going with Chapter 3. But we got to finish up Chapter 2 today, so Section 2.4, I don't even remember what it's on. Section 2.5 is marginal cost and marginal revenue. Eric, I got a blue TI for you. And hang on, here's the exam. Okay. So I'm going to have office hours today from 3 to 4:30. There's a homework assignment on sections 2.3 to 2.5, which is due on Tuesday, March 1. I also posted a homework for the material which we're going to cover on Thursday of this week, which will be due on Thursday of next week. Okay, so those are already up if you want to take a look at them. The next quiz is going to be on Tuesday next week, so 1 week from today. And it'll cover sections 2.3 to 3.2. Okay, so 2.3 was back when we were talking about, I think, tangent line approximation. And 3.2 is going to be up until we learn like a handful of derivative rules. The Chapter 3 notes are also on Blackboard. Okay, regarding the exam, the average score was around 36. So if you performed, average or a bit better than average, I think you could be pretty happy with your score. I posted a solution to the exam on Blackboard. So if you'd like to compare what you did on your exam to what was the correct solution, feel free to check that out on Blackboard. I didn't post a video on it, but if you have questions on any of the solutions, then just come and talk to me during office hours or shoot me an email or something like that. Any administrative questions or comments before we start today? No? Okay, well, I got one more thing to talk about, which is I did get some anonymous feedback, and anytime I get anonymous feedback, I just want to talk it over with the class so that, I just want to be as transparent as possible. So the feedback I got was the exam was different than the practice exam, which I didn't feel like was totally fair. To be honest, just because I did try to mention during class multiple times and during the solution video for the practice exam that, the practice exam is not really meant to be a direct indication of what's coming on the exam, okay? So it's definitely not a situation where I'm just going to change up some of the numbers and then that would be basically the exam. But what I do guarantee is that the topics of the practice exam are going to align closely with the topics of the exam. Okay, so I think I double-checked the exams, and I think there was one question, the supply and demand question, I think was the only thing that we didn't really talk much about supply and demand on the practice exam. But everything else was something that was covered on the practice exam. So, like I said, the questions are going to be different, but the topics will be the same. Okay, but I still want to give that student something. So here's my promise to you. For the next exam, okay, in addition to the practice exam, I'm going to post a bulleted list, okay, of topics which will be covered on the exam and, some things to know, okay? So like that list will include, okay, you need to know how to find the equation of an exponential function given 2 points. You need to know how to do this, do that, do that, do that. Okay, so I'll post that list, and you can use that in addition to the practice exam in order to help flesh out your studying and make it a bit more comprehensive. Does that sound fair? Okay, cool. All right, then let's go ahead and jump in. Actually, before I get to section 2.4, I just want to quickly remind us what we were talking about in section 2.3. So let's just remind ourselves where we were. So basically, in chapter 2, we started kind of talking about derivatives. Okay, in fact, I'm going to go all the way back to section 2.1. So in section 2.1, we had this novel idea of, well, how do I compute the slope of a function which is curvy? And the answer is, well, you take the slope of these secant lines and you move the secant line to be closer and closer and closer to just a single point. And you look at the slopes of all of these lines and you notice that they're getting very close to some number, and we can assume that that number is the slope of what we call the tangent line, which was this straight line that just comes in and barely touches our function at one point and then goes on in the same direction that our function is going at that particular moment. Right? So that was kind of how we thought about the instantaneous rate of change, okay, or the derivative of the function at a point, okay? So instantaneous rate of change, derivative of the function at x equals a, slope of the tangent line at x equals a, all of these are synonymous with one another. Okay, so that was what we were talking about. And let's see, section 2.2. Okay, section 2.2, we started thinking about, okay, well, what's going to happen when our derivative function, when is our derivative function going to be positive or negative, right? And so we noticed that, well, if the derivative is telling us about the slope of the parent function, then if the parent function is increasing, then the slope of the tangent line is going to be positive. So we can expect that the height of the derivative function is going to be positive when the original function is increasing. Likewise, if the function is decreasing, then the derivative is going to have a negative height. Okay, so that was increasing and decreasing. Okay, what else? Yeah, I guess one other important topic was knowing when is this derivative going to be 0, right? And it's going to be 0 exactly when the slope of the tangent line is 0. And the types of lines whose slope is 0 are, of course, horizontal lines. Okay, so we noticed something about this derivative being 0 is often corresponding with, okay, a peak or a valley, okay, or a max or a min. Okay, that's going to come into play a lot later. Okay, then we talked a little bit about Leibniz notation, okay, just a different way of writing derivatives, okay. And then we talked about tangent line approximation, which was this kind of interesting idea, which was to say, look, I noticed something similar between the tangent line and the function. Okay, and the idea behind the tangent line is at this point, it has the same height, and it's very briefly going in the exact same direction as our function is going. So if I want to know what is the height of the red function nearby to this point a comma f of a, then I can actually approximate it by the tangent line. Okay? So the way we wrote that down mathematically was when x minus a is small, okay, so when our x value is very close to a, then the function is going to be close to the tangent line. Okay, that makes sense, right? You can see when we're in between these two pink lines here, right? The tangent line and the function are very similar. And they only start to get very different, you know, further away, right? Like over here. See what I mean? So any questions on the first 3 sections of chapter 2 before we jump in on section 2.4? So anything about our ideas about derivatives so far, tangent lines, starting to think about the graph of the derivative function. Is there anything about that maybe a student in the class feels like could be a little bit more clear? Yeah, Gino.
Can you go over the increasing and decreasing the derivative again?
Yeah, sure. So, in fact, that was a question on the exam. So let me go show you what was going on that question really quickly, because that's a good opportunity to show. Okay, so we have this graph of g here, right? This was on our exam here, and we were asked to find, well, for which values of x is the derivative equal to 0? Well, we know the derivative, okay, is the slope of the tangent line. So in this circumstance, we just want to find the x values, which correspond to a point on the graph where the tangent line is horizontal. Okay, so those can be seen as the peak and valley of this particular graph. And then we're asked, okay, this is the pertinent question for Gino, is for which values of x is the function increasing, and which values of x is the function decreasing? Okay, so I highlighted them here in red, right? When the function is going down, in the sense of, okay, we move from left to right. So when the function's going down as we move from left to right, the function's decreasing. Okay, so that can be seen in the red region here. Okay, and then you can see here in the green region, that's where our function is increasing. As we move left to right, that's where our function is going up. Okay, so the slope of our function, okay, so what is like the pitch of our function? Okay, this is telling us what is the value of the derivative. Okay, so if we take a look at some various points here, like here, the slope of the tangent line is quite steep, right? So if we were to characterize this slope with a number, it would be a big number, as it compares to, say, maybe this slope, right? This slope is not as big of a number, but still positive, right? So the way we see that in terms of the derivative is, can you see the derivatives at the bottom of the screen there? Okay, let me show you in terms of highlighting what's going on here. So this green portion here, okay, the derivative is positive, but it's getting closer and closer to 0. We know the derivative is 0 here. It's positive here, and it's becoming 0, right? So on our derivative function, it should have a positive height, and the height of the function should become 0 as we move forward, right? So that's how we see the graph of the derivative. And then the part where the function is decreasing, we know that the slope of the tangent line will be negative, right? The slope is going down. That means it's a negative slope. So that means that the height of the derivative function will be negative. So that's where we get this part. Okay, but as we can see down here, yes, it's negative, but down here it starts to become more flat. And then it's eventually 0, okay? So the part where it starts to become more flat and becomes 0 corresponds with the part of the graph of the derivative where the derivative is becoming closer to 0 in terms of its height. Okay, and then lastly, we have that other increasing section, right? Where the slope is, in this region, is gradually becoming more positive. Okay, so that's how we relate the graph of the derivative to the graph of the function. Does that answer your question, Gino? Okay, great. Yeah, I think it's good that we ask these questions. I don't mind spending a little extra time going over some concepts that maybe weren't totally clear. So does anybody have anything else we want to discuss before we jump in? Yeah, Brendan?
It's specific to this question, but how would you know that the points over these intervals were closed or open?
Great question. So the question is, and I don't think I took off for points for this. If I took off points on question 1 for having a bracket or something like that, then come see me. I'm pretty sure I was lenient in terms of that. But the question is, when should we have a closed bracket versus an open bracket? So can anybody answer Brendan's question and tell me why I used an open bracket for the x equals 0 case here when I was describing where is this function increasing and decreasing? Shania?
So the closed brackets are when that x
Fantastic. Okay, that was a perfect description of what's going on here. So just to repeat what she said, Shania said that we should use a bracket when we include that point, okay, in the interval. If we include the point 0 in this interval, then we are saying that the function is increasing when x is 0. But what is our function doing when x is 0? It's not increasing or decreasing. So this is why I use a parentheses rather than a bracket. Okay, great question. All right, I think we should maybe start class at this point. But if you have some more questions, I'd be happy to talk about them during office hours today from 3 to 4 p.m., 3 to 4:30 on Microsoft Teams. Okay, so let's jump into section 2.4, which is basically about the second derivative. Okay, so this is like, I don't know, that movie Too Fast, Too Furious. We're gonna get twice as bad as it was before. No, just kidding. It's not that bad. But we got a function here, okay, and we know we can talk about the derivative of that function, which tells us whether that function is increasing or decreasing, right? But we also know that we can make a picture of the derivative, right? The derivative is itself a function. So the motivating question here is, what if I wanted to know when is the derivative increasing or decreasing, right? We could say that as well by saying, well, I want to take the derivative of the derivative, okay? Or the derivative of the derivative of the derivative, right? We can just carry on this process as long as we always get something which is differentiable. Okay, so let's just remind ourselves really quickly with this warm-up problem. We'll just do A, B, and C. How about that? Okay, so at these 3 points, we want to ask ourselves, what is the value of the function and what is the value of the derivative? Well, the function's pretty easy. I think the height here is pretty clearly a negative height. So I would say it's less than 0 at A, it's equal to 0 at B because the height is 0. And then again at C, I think it's less than 0 again, right? But the important part of this question is, how do we fill out the next 3 parts? So f prime of x, remember, tells me about the slope of the tangent line. So if I were to draw in a tangent line, and I say this number here is the slope of this line, do we think it's going to be positive or negative? Yeah, positive, right? Because the function is increasing. Okay, so we say positive here. How about at B? What do we think? Yeah, I think equal to 0 in this case, because the tangent line would look like this, right? Okay, how about at C? Yeah, negative at C, okay? So great. Just recall briefly, when is the derivative going to be positive, negative, or 0? So you can try the rest at home if you want to get a little extra practice with that one. Okay, but here's what I want to briefly mention. So, okay, if my screen will move. So, and I'll go slow here since I wrote some stuff out in advance. Okay, so for concavity, we already kind of mentioned how to look at a picture and tell whether it was concave up or concave down, right? But now we're going to give a much more concrete characterization of when is a function concave up or concave down. Okay, so we start off by this notion which I just mentioned, which is to say that, oh look, since the derivative is a function, we can also take the derivative of the derivative. Okay? Okay, so if I take f of x, I can find its derivative f prime of x, and then I can take that a step further and take the derivative of the derivative. Okay, and the way we do that notationally is to use two apostrophes, f double prime of x. Okay, this is how we say it. So f double prime. Okay, that's what we say. Okay, so the way we characterize f of x as being concave up is in the following way. So far, for concave up, what we've said is, well, the graph should essentially be bending upwards, right? Or if you were driving a car along this path, you'd be turning the steering wheel in a certain direction, right? So we're bending upward. So let's think about what that means for f prime of x. Okay, so this is the function. And remember, f prime of x, okay, is going to represent the slope of the tangent line. So as we move forward along this thing, why don't I draw this with actual pen? As we move from left to right along this thing, I want to ask you, what is happening to the slope of the tangent line as we move from left to right? Yeah, what's the word, mathematical word we have for something which is negative and becoming more positive? That's right, it's increasing. Okay, so we notice now we can actually characterize concavity in a more concrete way, right? If the function is bending upwards, then the mathematical way of saying that is to say that the derivative is increasing. Okay, so f prime of x is increasing. Okay, now I want to ask a student to really go for gold here. If I know that a function, f prime of x, is increasing, what can you say about the derivative of that function, f double prime? Not decreasing. Eric?
Positive.
Is positive. Bingo. Very good. Okay, so if f prime of x is increasing, right? If a function is increasing, that means that function's derivative is positive. So if the function happens to already be a derivative, if the derivative is increasing, then the derivative of the derivative should be positive. So this tells us the characterization of what it means for this function to be concave up. Okay? And the way we typically actually check this in practice is we check, well, is the second derivative positive? Okay, that's how we typically check it. Okay, but the second derivative being positive is equivalent to the first derivative being increasing, which is equivalent to the function being concave up. So typically, this is what we check. Okay, and let's just see what it looks like if it's concave down really quickly. Well, concave down, remember the n in the word down is kind of what it looks like, okay? So this is a concave down graph. And you can see the derivative, the slope of this tangent line as we move from left to right is going from being positive to being 0 and then being negative. So the fancy word we have for a function which starts positive and gradually becomes more negative is it's decreasing. Okay, so that's what we put here. F prime of x should be decreasing if the function is concave down. And that tells us that the second derivative will be less than 0. Okay, less than 0. Yeah?
If you kept taking the derivatives like over and over again, would it eventually just give you like a consistent like function?
It depends on what your original function is.
Okay.
If your original function is a polynomial of degree n, and you take n derivatives, you get 0. And from thereafter, you just keep getting 0, 0, 0, 0. But if your function is, say, an exponential function, the story might be a little bit different. But we might be getting a bit ahead of ourselves. But I like that you're going in that direction, because we're going to talk about that. Okay, so any questions on concavity so far? All right, so let's really quickly do a spot check on the first problem. We'll do A, B, and C again. Actually, why don't we do, I don't know, we'll do A, B, C, and D. Okay, so what we want to do is reconsider the graph in the warm-up problem, and we want to check whether the function is, the second derivative is bigger than 0 or equal to 0 or less than 0. So let's start with point A, okay? We want to ask ourselves, what is the second derivative sign? So the second derivative will be positive if the function is concave up. Second derivative will be negative if the function is concave down. So let's check point A. What do we think for point A here? Do we think our function is concave up or concave down at this point? Yeah, concave down. So what does that tell us about the second derivative? It's negative, right? Because the slope of the function is decreasing. So for this one, I'd say less than 0. Okay, how about point B? Point B is the point where we turn around. What do we think about the concavity at point B? Someone says still negative. Does anybody say 0 or positive? Yeah, I think this is a really tricky one to see, okay? But what you want to think about in terms of concavity, okay, is we always want to think about how is the function bending, okay? So this is trying to trick you because the function's going through 0, right? But think about how it's bending. If I draw a little bit of a picture here, what does that make you think? Well, in this case, we want to think about whether it's bending, right? So does this look like concave up as in U or concave down as in N? Right? This one looks like concave down. So this is actually still concave down. So second derivative is still less than 0. What would be 0 at this point is f of x and also f prime of x. Okay, because the slope of the tangent line is 0. But when we're talking about concavity, we're talking about what's happening to the slope as we move from left to right. And as we move from left to right, the slope is going from positive to 0 to being negative. So the slope is still decreasing. I know this takes a little bit of practice to get used to, but after you do, yeah, go ahead.
Would it be like accurate to say that it would like be helpful to look at it as in like the concavity of like the points on either side of B, like from A to C?
Yeah.
Or is that kind of, it only works in that case? And it's, I don't know.
Yes, but we should be careful, and if we want to be really accurate, we should use a very kind of small interval. Okay, so maybe not all the way from A to C, because if you go too far, you're going to run into an issue where the function has then become a different concavity, right? So you want to stay nice and close. But generally, yes, it's about what's the function doing kind of nearby that point.
Okay.
It's a little bit hard to tell just from looking at it, like what it's doing. But that's the same with the derivative, right? Because this function could come up through here and then go like this, right? And then the derivative at that point would be positive. You got to think about what's happening generally a little bit to the left and a little bit to the right to understand what the derivative would really look like. Okay, great question. I really like that. All right, let's try C and D. So next up, we want to tell what is the derivative doing at C. So if it's concave down, it should be negative, and if it's concave up, it should be positive. So what do we think about the function at the point C here? Okay, now let me draw some tangent lines here. Okay, so here's a tangent line, and here's a tangent line. And here's a tangent line, right? And then here's another tangent line. Here's another tangent line. So let's think about what's happening to the slope. The tangent line slope is becoming more negative, right? And then the tangent line here is like this. And then what happens to the slope of the tangent line? It starts to become more positive. Okay, so the slope of the tangent line is decreasing until this point. And then the slope of the tangent line is increasing. What do we make of that? Yeah, if the slope of the tangent line is decreasing, then that means that for this region, f double prime is less than 0. But for the next region where the slope of the tangent line is increasing, it's concave up in the next region, right? So in this region, we have that f double prime is larger than 0. If you have a continuous function which is less than 0, and then suddenly it's larger than 0, what must have happened in the middle? Yeah, it had to be equal to 0. Exactly. So I think it's a little bit tricky to identify these, okay, the first time you see them. But this point here is what we call an inflection point. Which is a point where f double prime goes, f double prime changes sign. So it either goes from being negative to being positive or being positive to being negative. Okay? And if f double prime changes sign, then by necessity, f double prime equals 0 at any inflection point. Okay, to make matters more confusing, it's possible for f double prime to be 0 without having an inflection point. That looks really funky on a graph, but we'll talk about that a little bit later. So I think f double prime is equal to 0 at C. And how about at D? Oh, whoops, I went too far. What do we think about D? Concave up or down? Concave up by inspection, which tells us what about the second derivative? Positive. Very good. Oops, I don't need the 0. Okay. Check how I'm doing on time. Okay, I'm good, I think. All right. So let's see maybe another example. Okay. Oh, this is a great problem. This is a great problem. Problem number 2, okay, which asks us, okay, for each of the following, what we want to do is sketch the graph of a continuous function. Okay, it means I can draw it without picking up my pencil, right? And it needs to satisfy all of these conditions. So the first function, we need to have that, let's just focus on part A for now. Okay, let's focus on part A. And I want you to try this on your own first, okay? So let's take like 2 minutes to try and produce a graph on our own, okay, that satisfies these 3 conditions. Okay, so remember, f of 2 is larger than 0 means the function height is positive when x is equal to 2. And if f prime of 2 is larger than 0, that means that the function is increasing at x equals 2, right? And f double prime of 2 is less than 0, so the function should also be concave down at x equals 2. So let's try to draw the graph of a function on part A that satisfies all 3 of those conditions. And just take a couple minutes and do that individually and see how it goes. anybody like a little bit more time to work? Okay, I'm seeing some nodding, so let's take about another 30 seconds. Try that out. If you already finished, try working on B and C. All right, let's try to come back together as a group and see if we can come up with a reasonable picture just for part A, and we'll go through this kind of slowly. Okay, so one thing that I sort of immediately notice about all three of these conditions is that they all have to do with when the x value is 2. Okay? So really, the only information that I get about this function is that I get some information about what the function is doing when x is equal to 2. Okay? So I just get some information about this little snippet of the function from when x is equal to 2. Okay? And let's see if we can come up with these rules one by one and see what they mean. So who can interpret f of 2 is larger than 0 in terms of the graph of our function? Who's going to tell me what that's going to do for our function here? Well, if the function is positive, what does that mean about the graph? Yeah, Christian?
Like whatever point you're plotting, or whatever point like your graph crosses over, like x equals 2 is going to be above your x-axis.
Very good. Whatever point the function is at, whatever the height of the function is positive, right? That's essentially what we're saying. So if this function should pass through a point when x is equal to 2, and that point should be in the first quadrant. Okay, so this is the first quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant, right? What it's telling us is, well, actually it's positive, which means that the function height should be somewhere in here, in the first quadrant. So I'm going to put a point, I don't know, there's a point. Here's a point where the function height is positive. So far we've satisfied the first condition. Now, the second part tells me that my function at that point should be increasing. So let's revise our graph to satisfy these two conditions. If I just have a function which is larger than 0 at that point and increasing, well, increasing means as I go from left to right, the function is going up, right? So here's a function which satisfies the first two criterion. How about the last criterion? Does it solve the last criterion? No. How could I modify this a little bit to make it solve the last criteria as well?
By turning it into a curve.
Yeah, it should be curvy, right? Not just straight. If it's straight like that, that means the second derivative is equal to 0. So it should bend, okay? Should I bend like this, or should I bend like this? What do we think? Okay, this is 2 and this is 1. Hands up for 1. Hands up for 2. Okay, lots of people. Great. So we're getting this really well. Okay, so we can fix this by just adding a little bit of a bend. How about like that? Okay, then the function's increasing still, but it's bending downwards, okay? And the height of the function's positive. All right, let's have some thumbs up for how did we do. Thumbs up if you had no trouble doing that exercise on your own. Thumbs down if you needed a little bit of help. or thumbs in the middle if you're somewhere in the middle. Okay. Well, it's a little bit of a tricky exercise. I think this is what we call a high cognitive task, so it's tough. Let's go through the next two together. So for B, I want to satisfy these conditions at 3 different points. Okay, so a little bit interesting. So it says the function should be increasing at 0, but they don't tell us whether the function should be positive or negative. They also tell us that the function is decreasing at 0, and it's increasing at f prime of 3. So the function should be decreasing initially and then increasing. And we also need that the function value at 1 is positive. So all I need to know is that the function value at 1 is positive. So how about I just make this look like this? I can just bring it in like that. Okay, if I did a function like that, then let's double check. Is the function decreasing when x is equal to 0? Yes. Is the function increasing when x is equal to 3? So that's this point. Yes. Is the function positive when x is equal to 1? Yes. Okay, so that's how we can kind of go through these steps one by one. Okay, I'll leave the last one as an exercise for you. I think it's the hardest one. Give it a shot on your own at home and let me know what you think. Okay, we're going to move on and talk about concavity with tables. Okay, so we also want to know, okay, how can we tell whether a function is concave up or concave down given a table of inputs? Okay, so we don't get the picture. We don't get to look at the picture and say, well, it kind of looks like it's bending down, so it's concave down. You know, we just get a table, and I don't really know what the graph of a function like that is going to look like. So the key idea here is to remember this fact. So who can fill in the blank for me? If we have a second derivative is larger than 0, can someone tell me what that means for f prime, the first derivative? What's happening to the first derivative if the second derivative is larger than 0? Yeah, very good. It's increasing. Okay, if the derivative is positive, then the parent function is increasing. So that's how we fill in this blank. So, how to tell if a function is concave up or down given a table of inputs? The key idea is to remember that the second derivative being positive means that the first derivative is increasing. Okay, means the first derivative is increasing. All right, so how do we implement that in practice? In practice, we check if the rate of change is increasing or decreasing. Okay, so we want to know whether the second derivative is positive or negative. So to do that, we check if the first derivative is increasing or decreasing. The way we do that is we're just going to check the rate of change over each of these intervals, right? And we're just going to take the average rate of change over these intervals and see what's happening. So for this one, we're going to take the average rate of change over each interval. The first one we go up 1 over 1, so it's 1, right? Second one we go up 2 over 1, so that's 2 over 1 is 2. The third one, what do we do? The snowfall went up by 3, right? So the slope of this would be the rise is 3, and the run is our independent variable t went from 3 to 4. So to do the average rate of change, we do 8 minus 5 over 4 minus 3, right? Which is just 3 over 1, which is 3, right? So that's how we get this is 3. Okay, so what are we thinking so far? Okay, well, we know generally that the snowfall from week to week is increasing. But who can tell me what it means? Well, first of all, who can tell me whether the second derivative is positive or negative for this first region? Our rate of change went from 1 to 2 to 3. So the slope of our function went from like slope 1 to slope 2 to slope 3. What do we think? Concave up or concave down? Yeah, concave up in this case. So for this region, f double prime is larger than 0, right? Okay, so I just want to focus on these first 4 weeks and ask, how can you characterize f double prime is larger than 0 for the first 4 weeks in terms of the problem? So f double prime of x is larger than 0 on the interval from 0 to 4. What does this mean in terms of the problem? That's the question. Any brave soul want to take a shot at it? Yeah, Christian?
So that portion of it is concave up.
Yeah, the function is concave up, but what does that mean for the snowfall, Annabelle?
That it's gradually increasing the amount that snows.
Yeah, the amount of snow is increasing. That's true. We went from 2 to 3 to 5 to 8. Shania?
Isn't that the amount of snow is growing instead of decaying?
Yeah, the amount of snow is growing is still kind of the same idea of increasing versus decreasing, but what does the second derivative tells us? The first derivative tells us increasing or decreasing, but the second derivative tells us concavity, which tells us whether the first derivative is increasing or decreasing, right? Anybody got another idea? Gino?
The period before right now, it wasn't snowing, but not about to snow a lot.
Yeah, I think we're dancing around this idea. Brendan?
Is it about the rate?
Yeah, it is about the rate at which the snowfall is increasing. Not only is the snowfall increasing week after week, but the rate at which the snowfall is increasing, it's increasing faster and faster and faster. That's what's happening here, okay? This is kind of like an acceleration kind of idea, okay? The snowfall is increasing, but the rate at which the snowfall is increasing is also increasing, which tells us that this, this curve looks kind of like this, okay? It's not just that the snowfall is increasing day after day or week after week. It's increasing, and it's increasing faster and faster and faster. That's the characterization of this for this problem, which is really tricky to see for the first time, okay? So don't feel bad if you don't quite get this yet, okay? This is a challenging problem to ask. So thanks for everybody who participated. Okay, so this is basically all I wanted to communicate about this. So you can try this actual problem if you want. Okay, so I should briefly mention the second part, okay? So let's just modify this problem to during the first 4 weeks. Okay, so forget about calculating the average rate of change. Okay, so we noticed something about the second derivative, right? Now, I just want to mention this notation here, okay? All this notation means is do the second derivative of s with respect to t twice. So this just means s double prime of t, okay? That's all that this notation means, okay? This is called Leibniz notation. For second derivative. So, s of t becomes S prime of t, becomes S double prime of t. This is our Newton notation. It's the same thing as doing S becomes ds dt becomes d2s dt squared. All right, so this is just how we do notation. So what can we say about the sign of the second derivative during the first 4 weeks? Well, the rate of change in the function is increasing. If that tells us that the second derivative, which is the derivative of the derivative, is going to be positive. So we can say the second derivative is positive in those first 4 weeks. Okay, so let me fix my notation from before. I put f here. I should have put s. And in this part, I should have put s of t, s double prime of t. Sorry about that. I got ahead of myself. Okay, any questions on this problem? Okay, seeing concavity in the table is just about checking whether the rate of change is increasing or decreasing. Okay, so yes, we can see the numbers are going up, but are they going up faster and faster and faster, or are they going up more gradually as we move forward, or are they decaying faster and faster and faster? What's happening there? All right, any questions on anything second derivative related? So finding second derivative based on a table, seeing the second derivative based on the graph, interpreting the second derivative in terms of what is the first derivative doing, what is the function doing. Yeah, Brendan?
Have we talked about what happens if the second derivative is 0?
Yes. So if the second derivative is 0, well, we had an example of when the second derivative was 0. It was happening here, right? So the function was concave down, and then suddenly it was concave up. So we saw that the second derivative had to go from being negative to being positive. If you have a function which is negative first, right, and then it's positive, then what happened in the middle is you must have crossed the x-axis, right? So for this example, this was a situation where the second derivative was 0 at that point. But it doesn't necessarily have to look like that. You can have a function like, and this is getting ahead of ourselves, but if f of x equals something like x to the 4th, okay, then this function looks kind of like a flatter-ish parabola, okay? It gets kind of flat towards the origin. And it's actually true that this function is concave up everywhere except for at x equals 0. At x equals 0, this function is actually has no concavity because it kind of flattens perfectly out is basically what happens. So at 0, there's actually no curvature to this thing. But that's just a sort of a special circumstance where it's possible for the second derivative to become 0 without necessarily saying we're changing from concave up to concave down. That's the point I'm trying to make. But that's a subtle thing, which we'll talk about a little bit more later. For now, you can think of second derivative equals 0 basically means that the function at that point kind of flattens out and has no curvature temporarily. Great question. Annabelle?
So like if you're given a table, like the second derivative equal to 0, you have to like look at what the second derivative was before and after to like figure out if it's concave up or not.
Yeah, exactly. So if we go to this table here, okay, we can see, okay, what happens. The function is increasing and concave up, right? And then it hits a peak at some point, and then it starts decreasing, right? So our function is like increasing and then decreasing, right? So, oops, shouldn't look like that. Our function is like increasing and concave up, And then later on it's decreasing and I think concave down. Or is it concave down? No, it's actually decreasing and concave up. So this is a bad example of a table. But what you would look for in terms of a table is if the first derivative is increasing and then later the first derivative is decreasing, then that tells you then at some point in the middle the second derivative must be 0. But again, this is a subtle thing, and that's maybe too complicated of a question to ask based on a table, I would say. Okay, great. I want to move on here and talk really quickly about one more thing. We're going to do section 2.5. It won't take us long at all. And just talk really quickly about marginal cost and marginal revenue. Okay, so this was something that there was a little bit of confusion on the exam for. So before, okay, we define marginal cost and marginal revenue, okay, to be the slope of the cost or the revenue functions, respectively. So for this problem, in part A, okay, a company selling radios, they pay $12,000 per year for office space, and each radio they make costs $7, right? So in this case, their costs, okay, are going to be their fixed cost, which is $12,000, plus their variable cost, which is $7 per radio that they make. So 7 times Q, where Q is the number of radios that they make, right? So if I want to talk about the marginal cost, it's the slope of the cost function. So for this problem, I would say that the marginal cost is equal to 7. Okay, but I wouldn't put a Q here. A lot of people put a Q there. You could put a Q if you were talking about the variable cost. But the marginal cost is specifically addressing the rate of change of the function, which for our function, if it's linear, it's going to be the slope. Okay, so we would just use the number 7. And if we wanted to give units, we could say dollars per radio, right? Okay, so that's how we think about marginal cost in terms of a linear function. Now, if we have a function, a cost function, right, you may expect that maybe the more items I produce, the less it costs, right? For example, because I can buy my supplies in bulk, maybe, right? So you might have a cost function which isn't necessarily just a straight line, right? A cost function could be curvy in all sorts of ways, right? So we want to still be able to talk about marginal cost and marginal revenue. Now, if I started by defining marginal cost and marginal revenue as the slope of a line, and now I want to characterize marginal cost and marginal revenue for a curvy cost or a curvy revenue function, what kind of topic do you think we're going to use for that? Sorry? So we're talking first about the slope of a line, but now we want to generalize that concept for a curvy function. Yeah, well, average rate of change or instantaneous rate of change, right? We want to talk about the slope of a curvy function, which is the whole idea behind the derivative, is to describe the slope of a curvy function. Okay? So now what we're going to do is just the following. The marginal cost, respectively revenue, is defined to be okay, if you've never seen this symbol, that's what that means, is defined to be. Marginal cost or marginal revenue is defined to be the derivative of the cost function, respectively, the derivative of the revenue function. Okay? So that's all that marginal cost and marginal revenue really are. They're just the derivative of that function. Okay? And the derivative of any linear function is, of course, just the slope of that function, since the rate of change of a linear function is constant. So this generalizes the concept which we talked about in, I don't know, section 1.4 or something like that. It's been a while. But this is how we talk about marginal cost and marginal revenue for cost and revenue functions which may be nonlinear. Okay, so one thing that is talked about in the book, and you'll probably see it in your homework some, is how do we approximate the marginal cost or revenue, okay? And the way we want to think about this, okay, is we give this sort of a natural motivation. Okay, we give this a sort of natural motivation. So let's say I have a cost function. So here's Q, and here's C. So C of Q is going to be a cost function. Let's say I have some fixed cost. Fixed cost, the way I view it is, well, I have a cost for producing 0 items, right? The fixed cost is what I have to pay to set up shop, right? And then from there, it's going to cost me a certain amount per item to make. But maybe if I make a lot of items, I get a discount. So maybe it's curvy, kind of like this, right? So this could be a cost function. And what I want to know, okay, is if I pick a given Q naught, how can I approximate the marginal cost, which again will be visualized as the slope. Okay, so marginal cost at Q naught items, or okay, we say marginal cost at Q naught items, or when producing Q naught items. Okay, this is the terminology we use, is defined to be C prime of Q naught, which is the slope of the tangent line, seen in blue here. Okay, so this is the visualization of what we're doing here. And the really natural way to approximate it is just to then take, okay, what if I increased the number of items I'm producing by 1? Then I could draw a secant line, which would look like this. Okay? And the secant line, if I just increase the units by 1, it doesn't increase the cost very much, and it's going to be pretty close to the slope of the tangent line. So I say that this is approximately equal to the slope of the secant line, which is equal to C of Q naught plus 1 minus C of Q naught, all divided by Q naught plus 1 minus Q naught. Well, if I take Q naught, I add 1, and then I take away Q naught, I'm left with just 1, right? So this is just C of Q naught plus 1 minus C of Q naught. Okay, so what is this saying? This is roughly a characterization of how much does it cost to produce the Q naught plus 1th item? So let's say I've already produced Q naught items. I want to know what's the cost to make one more. Well, that's just the cost to produce Q naught plus 1 items minus the cost of producing the first Q naught items. Does that click? Okay, so that kind of tells me, well, what's the price to just produce one more item? And the idea is that the price to produce just one more item is probably going to be just about equal to the marginal cost, i.e., how is the cost changing? Well, we ask ourselves, how would it change if we added one more item? And that gets us pretty close. So this is the way that we approximate the marginal cost or the marginal revenue. Okay? So to approximate, we use the following. C prime of Q naught is approximately equal to C of Q naught plus 1 minus C of Q naught. Okay? Same deal for R, right? R prime of Q naught is approximately equal to R of Q naught plus 1 minus R of Q naught. Same deal for profit, okay? So there's absolutely no difference between marginal cost, marginal revenue, marginal profit. They're all defined to be the rate of change of the cost or the revenue or the profit function. Okay. Also works for profit, pi of Q. Okay, so very natural idea. In section 1, we came up with, we started by learning about linear functions. And then we said, okay, let's learn about cost and revenue when the cost and revenue functions are linear. Now we're learning about Curvy functions. And we say, okay, what if cost and revenue are Curvy functions? And we just extend all the theory which we've already learned about derivatives to cost and revenue, okay? And the only thing that's different in this section from all of the stuff we've done before is the terminology, okay? The terminology is when you hear the words marginal cost, okay, you should be thinking derivative of cost function. Okay, that's just a fancy way of saying derivative of the cost function. Any questions on marginal cost, revenue, profit so far? No? Okay. Let's see a quick example of some cost and revenue functions which aren't linear. I was going to have us do this problem as a group, but I don't think we have enough time to do that. So we'll go through them together. So this is problem number 3. Okay. Pretty standard problem. In fact, the first part doesn't even talk about marginal cost or marginal revenue, but let's do the first part together. So we have the cost and revenue function. So the cost function here can be seen in red, right? And the revenue function is this blue one. Okay, where Q is in thousands of items and the price is in thousands of dollars. So for each production level, we're supposed to state whether the function is going to make a profit or whether the function is, or whether the company is not going to make a profit, and whether they should increase or decrease their production. Okay, so let's start with 500 items. Well, if it's 500 items, that tells me that Q here is equal to 0.5. Okay, why? Because Q is in thousands of items. So if I'm producing 500 items, that's exactly half of 1,000 of items. So I go to where I see 0.5 here. okay? And I'm interested in this region, right? What's happening to the cost and the revenue function here? So this is 500 items. All right, so which one is bigger, the revenue or the cost? Revenue is bigger. Is that good or bad? That's good, right? We want to make more money than we are spending, right? So in this region, we have profit, right? Profit is R minus C, which is positive in this region. So we are making a profit. How about the second part of the question? Should we increase or decrease production in order to increase profit? What do we think? Should we move to the right or should we move to the left in order to increase profit? Yeah, I think we should move to the right, okay? Because if we move to the right, this green line, which signifies our profit, gets bigger, right? The difference between the revenue and the cost gets bigger, okay? So even though the cost is growing, our revenue is growing faster. So we should increase. Okay, we should increase. And if you think about what that means in terms of the marginal revenue and the marginal cost, okay, what I said was it means that the marginal revenue, the rate at which revenue is increasing, the revenue is increasing faster than costs are increasing. Okay, so if the marginal revenue is bigger than the marginal cost, then my profits are going to increase as I move forward, right? Okay. So I'll leave the other two for you. But let's just really quickly do part B here on the second part. I just want to check, one spot check real quick. Is the marginal cost greater at q equals 10 or q equals 35 for this function? Well, q equals 10 can be seen right here, right? That's where q is 10. And q equals 35 is right about here. Well, what does the marginal cost mean in terms of this picture? You can tell me what's the geometric interpretation. Christian?
The slope at the point 10.
Exactly. It's the slope of the function at that point, or the slope of the tangent line at that point. So we got one slope here, and we got one slope here. So, is the marginal cost greater at q equals 10 or q equals 35? Yeah, q equals 35. Because the slope of this line is steeper. All right, great. I'm done for today. Thanks for your attention. If you have any questions, then hang out after class or come to office hours today from 3 to 4:30.